So Jen from Georgia Tech is going to give the next talk of the day. She's going to talk about piecewise linear surfaces in homology.
Thanks for the introduction. It's a pleasure to be here. Everything we're talking about today is joined with Matt Stoffregen and Hugo Zhou. Hugo will be a second PhD student. He's defending later this summer. Great. Okay. So that you know where we're going, I'll put a theorem on the board. It's okay if you don't know all the words from the theorem. This is from earlier this year. And so the theorem is that PL genus can be arbitrarily large. And so one of my goals for the next few minutes is to tell you what I mean by PL genus. But before I do that, let me just remind you of something. Okay, so one thing I want to remind you, so if we have a knot K in S3, we can make a cone on it. Right, you can put a cone on at n, e n plus 1, or the cone on this here is going to be B4, comma, a disk. So maybe like the cartoon picture, right? So here's S3, here's K, and then here's the cone. So the conclusion is that every knot in S3 bounds a piecewise linear disk in B. Right, and so one thing to note about this PL disk is that it's not locally flat. Right? It's that So today, when I say PL, this should be sort of the model in your head of what you think. Piecewise related, and it does not. Okay. So this is all not that we consider not mathematically. We consider PL versus the 4-ball. Well, it's not very interesting because that is that. So so what do we do next? We'll say, okay, what about not in other free manifolds? And then you say, like all free manifolds are too complicated. Let's think about non-homology here. So what about not in homology spheres? Okay, well, the free manifold bounds to the 4-manifold, and in fact, smoothly. And in fact, well, okay, if you allow any bound in 4-manifold, well, then in fact, you're not because some 4-manifold is not the bound smoothness. So let's also restrict the bounding. Okay. What happens? Not really well with that. We're going to restrict the bounding interval, and as maybe that's from the later list, but we're going to require that 4-manifold sphere. So what about not integer homology sphere is Y, where Y is boundary of some integer homology. Okay. And so that from now on, Y will always be an integer homology sphere, such that there's this integer homology all that. Back there. Studied this type of question for a while. And so one early result in this question absolute from the early 90s. Great. So this is that the homology here. Y. The Y is about to be an X, X is the infinite homology of. In fact, this is the X factor. In fact. So that K not bound. Yeah, then. So let me tell you what it is for. It's a pretty bad thing for the women neck. You prove that K is not bound a helix in X. So when you look at this list that I on in class,
Yeah. Yeah, amazing.
oh yeah. So, in particular, if anyone noticed any particular feature about, we just think about this the two black and white way. You know, anything about that nice property. It's symmetric. Yeah. So in fact, K is not bound with PL in the this one manifold X is bound to Y. But in fact, if you like it's symmetric, so you just switch the ball to one of the channel, and then it does in that way. So that's sort of the basis of the natural question of example and well, so this doesn't matter if it's in this one example, but what about if you look at all and so that upgrade was something that Levine provided in 2016. So okay, so he proved that there exists a knot K in an integer homologous of Y that bounds integer homology such that K does not bound a PO disk in any bounding integer homology space. And so he proved this result using the Heegaard Floer invariant pattern epsilon. And his example was just a slight variant on but then it's something for the which the water is symmetric, and then if you just connect the action or just okay. Okay, so we have these knots that don't bound any PL disk. And so, well, this motivates the following definition, which I'll call the PLZ genus. Okay, so this is just the minimum genus of sigma, where what sigma is some PL surface in X, where X should be a integer homology ball. Such that the boundary of the pair X comma sigma is Y comma. So we'll call this the PLV genus. Right, and so Adam's result is saying that there exist manifold-knot pairs such that this PLV genus is non-zero, right? They don't bound it. Okay, so this thing can be non-zero. So there's a natural question one might ask, right? The natural question you might ask is, can it be arbitrarily switched? And as advertised at the beginning of the talk, that's the result I want to tell you about. And the answer is yes, it can be arbitrarily. For any natural number n, there's a knot Kn, Yn, such that there's PLV genus. So now maybe you're wondering, okay, well, what are the manifolds? What are the knots? Yn. So Yn is the next sum of some surgeries. So -1 surgery are the 2n plus 2, 2n plus the Heegaard knot. Okay, and then remember that these Yn better valid homology ball. What is my favorite way to see that you can homology here? Build a homology ball. Well, just take the next up the one here. Okay. Now what about the knots? Okay. But in particular, well, our knots should not be local knots. It should not be knots that are gated at all. So what's my favorite way to get an interested knot and surgery on a knot? Well, one of my favorite is to take the meridian of the knot that I switched along. Maybe something like this. This case, not to be good enough. Okay, so what's my second favorite way to just not in surgery? Well, okay, well, you go back to the question. What's my favorite way to build knot? Do not build knot or change the cable of that knot. So this is my favorite interested knot. Surgery was cable. I think it's also down. So I called the meridian for search review, and then we three, this should just be this is the 3 Cable. So when I write new and I just need an and I just want cable. Okay. KN. So in the first command, I'll take the 2n plus 1 cable. And then in the second command, I'll just take the unadopted land. Right, so so on the knot level, nothing is happening in the second command. The second command is there. So those are our manifold knot together. So maybe one question you might have is, well, how do we study PL surfaces, right? So, you know, a lot of the tools we have coming from Heegaard homology and gauge theory, they're well equipped to study point surfaces, but they're not as well equipped to study piecewise linear surfaces. And so the following fact is going to be helpful for us for converting a question about PL surfaces to a question about smooth surfaces. But as we'll see, it also comes at a cost. So the fact that's useful for us is that, well, like what do these PL surfaces look like, right? So I started by telling you about taking the cone on a knot in S3, and I said that should be a model to what a PL surface looks like, and in some sense, that wasn't like a big lie at all. That was very close to the truth. So we can assume that our PL surface sigma is smooth, except for possibly finitely many singular points. And the singular points all look like a cone on a map. So each of which is modeled on the cone of a knot, say Ji in S3. So maybe the picture you should have in mind. So here's my homology ball X. Here's our knot K sitting in the boundary. And then we have our surface sigma. It's like mostly smooth, but maybe it has a couple of cone points. And then maybe it has some genus. Okay. And then you look at this and you say, okay, I don't like these singular points. Well, there's finitely many of them, so let's just remove a neighborhood of each of them. And then you say, oh, well, if I remove a neighborhood of each of them, I don't really like that either, because then I get like a bunch of S3 boundary components. So I say, okay, well, remove the neighborhood of each of the singular points, but then also just like choose them together. So just like remove like this. So now let's understand what we're left with once we've removed a neighborhood of all singular points and then connect it. So what did we do? I wanted to delete a neighborhood of a collection of arcs in sigma, connecting the cone points. So what do we what are we left with? Okay, so well, we started off with a homology. Wait, the boundary is wide. So now we're going to be left with the homology coordinate. We're left with the homology coordinate between the boundary y and, well, now on this inside here the boundary is S. So we're left with homology coordinate between F3. Right, so I guess we'll call this X naught, X minus. Okay, and then we have sigma naught, which is sigma minus naught. Okay, and now, well, what is this? This is okay, we got rid of all the singular points, so now we're left with this. And X naught, it has two boundary components. On this end, well, it's just the kinetic sum of all of the JIs. So co-bounded by, we'll call that J. And on the other end, we just have K and Y. Okay, and so maybe I'll redraw this picture to make it look like the way that I like to draw homology coordinates. Okay, so here we have on one end we have a straight, on the other end we have a line, and then we have some surface. Then we have J. So we made it like better, and then now everything inside is fluid that I know how to study within. We also made our life a little in the sense that now we have like no control over what does not say. Right, so we're happy that we're studying smooth surfaces and homology coordinates. We're unhappy that now, while we're looking at these coordinates to any object. Oh, but then if we color it, then we have to go.
I know, but I'm just saying that like it's as general as people, right?
Oh. That's, yeah, but like, if we study it from this perspective, it's like, we have to look at coordinates to like all not change.
Right, but for any such coordinate, we can also construct a TL base with the same genus inside of all. So like, it's a compound problem.
Yeah, it will go on, just like whatever they can right now. Now we have this. Then now I carry two yeah. We need to do that the minimal genus of any use the word in a multi-coordinate okay, and to K and Y and W. So what happened because we have to study it So, and maybe review this one. I know my favorite tool is Heegaard.
That question, that the manifold that is not for the manifold, they're found in fact.
Yeah, these manifolds don't have that again.
So you know, it's not your that they don't have like you don't know. And I could not turn.
Other questions? So, let me just remind you of the salient features of Heegaard Floer homology that we'll be using. It's defined by Oswald and Zhou. So, to a 3-manifold Y, we get a chain complex CF minus of Y. What kind of algebraic object is this? This is a finitely generated chain complex over a polynomial ring with one variable. The degree of U is -2. The chain homotopy type is an invariant of the 3-manifold. And in a special case that we're interested in, where Y is an integer homology sphere, the homology of this chain complex has a particularly nice form. There's a single 3 summand, and then some torsion. Right? Since these are finitely generated modules over a PID, you always know that it's going to decompose as a direct sum of 3 parts and torsion parts, and then because if you have an integer homology sphere, Oswald and Zhou will have exactly one 3 part. Okay, and then, well, 4-manifold cobordism between 2 3-manifolds induces a module homomorphism between the Heegaard Floer homologies. And particularly nice cobordisms induce particularly nice maps. So what do I mean by that? Well, for example, a homology cobordism induces a map that is an isomorphism on the 3 part of HF minus 2. If you're worried that this depends on the choice of splitting, here's another way of saying this is that this is an isomorphism when you share it. And so what we have not directly manifold, so you need a binary of this invariant that takes into account the not invariant manifold. There's a couple of ways to do that all eventually encode the same thing. The way that I'll do it is that, well, here what we've had are chain complexes over polynomial in one variable. Well, now we have a connected manifold invariant and finite general chain complex over a polynomial invariant. Okay, so if I have a not here, Y, I'll get the one called CSA, Y from the A. So this is a finitely generated bivalent chain complex over polynomial ring in U and V. So I have bivalent. So now we do -2 comma 0, and the degree of E is 0 -2. The chain homology type. You might wonder, well, what's the relationship between this invariant and the theta element? And so, yeah, so if you know what don't want to figure that out as well. U is kind of how they manage to do plots, say the base of D and U is kind of how W. So we said B equal to 1. That's like we're getting at it. This recovers just the Heegaard Floer for the ending example. And in fact, there's some symmetry between U and V. So if you said U equals 1, okay, well, if you said U equals 1, then you're going to get something that generated over F joining B. Well, you don't know that would be a variable, still something that's on and then develop. So now maybe now we have not here. Okay, and so now we're going to be interested in, well, what about if I have a surface cobordism inside of my four manifold? So maybe the picture something like this. So the cobordism of pairs W sigma from Y naught K naught to Y1 K. Okay, let's say that sigma is genus G. Okay. So remember, in this our knots are decorated with a pair of base points, and in fact, we also have to decorate our surface. So like one way to decorate a surface could just be, okay, so like here we all decorate right that way. I'll change. Okay, and you could decorate it in a lot of different ways. And if you already decorated it in a way that split the genus and sort of this genus 1 is the shaded part, genus 2 is the other part. You could use the shaded part and the shaded part, connect the two boundary parts with all the genus and the unshaded part. So the point is that, well, we want to consider non-negative integers C1 and C2 with that sum to be equal to G. And you should think about these integers as just telling you how much of the genus is in the shaded part, how much. Okay. Then this cobordism of pairs induces a map on these non-floor complexes. Wait, and then where did this CI come into play? They tell us what the bi-grading of this map is going to be. So it's minus 2C1, comma, minus 2. And then, if you have the added feature that if W is the homology cobordism, then you still have the staff as it's going to be an isomorphism on the free side. Questions? Yeah. Oh, you understand the stated. So, okay, for like technical reasons, these cobordisms are decorated. And you get to choose how you decorate them. Okay, and then you choose the split of the genus in any way you want. In fact, for the piece of here, we actually just decorated in such a way that all the genuses is one half of it. But sort of in the process of doing this theorem, it was very important that you could decorate it however you wanted to. Like if you use certain decorations, you get no obstruction, but if you use sort of in this situation, the right decoration. Other questions?
Decoration. It's not only for the genus.
It's not only for the genus, it's sort of for the, yeah, but for sort of for what we need with the sort of the development. Right, the goal is to say something about homology cobordism to activate. So we're going to use some special property that the homology cobordism to activate on any different homology here. And as is often the case in these things, well, what's going to be special about activate has a simple property of homology and HMI. So okay, and then one. You can turn out homology cobordism. So we have a homology cobordism, some not. J and K. Okay, and then we'll just by turn on homology cobordism around, well, we can get that back to K and in line. Wait, remember, this is not the concept, I said that we said you can that covers the initiating homology. That covers minus an energy example, so that mitigates covers. So the key point that we're going to see is that we're looking on this energy. And then we use that something who's equal one homology. So the special aspect that is going to be, and what's the actual special aspect of homology the special aspect is that you take non-trivial and add on you. Let's say non-trivial. That's like 10 attributes. So this would be an actuary. Okay, so you any not to be open. Okay. What's going to be even more to the way of saying this? Right, for homology is cycle mod batteries. So if you time something, well, it means that it's 0. Well, this actually implies that X has to be bounded. Okay, so imagine you're using like algorithm topology expressions. Like so let me give you a toy model about how you can use these ingredients to build an obstruction to the genus of a toward them to a knot, right? And like here, like this is sort of like holding acting out of that so here's a toy model. Let's have this complex Cn that's going to be generated by three things, A, B, and C. I like to draw pictures like this. I'll tell you what this picture means. So this is telling me that the boundary of B is u to the n B times A plus u v to the n B. Okay, this thing is bi-graded, so if you care about the grading, I can tell you what they are. Grading is 0, 2 minus 2n, 1 minus 2n, 1 minus 2n, 2 minus 2n. Okay, and then we're going to see what's possible for math. So we have this u and this v, and that's like too many variables for me to handle. Plus, we're factoring through something where we're setting v equal. We're going to, the only sort of interesting fact to know about it happens when we set v equal to 1. Okay, so let's look at what happens in this complex when we set v equal to 1. Well, if we set v equal to 1, then we see that u times u to the n minus 1a plus c. This is the boundary in Cn not b equals 1. Okay, well, as is a chain map, the chain map is boundary boundaries. So this tells us that u times u to the n minus 1 f of a plus f of c is the boundary in b not b equals 1. Right, and now we put it back here. Right, so this tells us now you can that u to the n minus 1 f of a plus f of c the boundary. Okay. Then you're gonna say like, oh, like I have two things add. I don't like two things add. Let's just get rid of this there. Let's just mod out by u to the n minus 1. Okay, so then how about that f of c? The boundary in d mod d equals 1 u to the n minus 1 equals okay, and now let's get back to Cn, right? Because we know very little about D, but if we get back to Cn, we have what the description of that entire thing. So just hit this G. So G f of C is the boundary in Cn mod B equals 1 e to the n minus 1 equals 0. Okay, and so well, in here, like this is still what we have kind of close the destruction hub. And so we can see that the only boundaries in here are okay, so well, anytime I have a boundary, right? These things are actually going to be modules, like it only takes a multiple then or a multiple. So the only boundaries in here are U and V multiples of U to the n minus 1a in UC. And then you can also compute the gradient of each of these things, right? The gradient of this is minus 2n 0, and the gradient of this is 2 minus 2n 2 minus 2n. So
we could have my point already 0.
Yeah. Oh, but this is basically like 0, you take off 0 to that. So this is 0. And then you look at, okay, so then from this you can conclude that there does not exist F and G of degree, we'll say each degree. Zero, comma. But you just sort of compare these to the gradient of C over here. Okay, and so I did my all here. So the point of this toy model is to show you that when you see things that look like this in your T complex, well, just using the fact that you know things about the V equals 1 homology of the spin manufacturing group, then using the gradient you can get an obstruction. Okay, so this is then the next question you might ask is, well, okay, how do we realize spin complexes like this? It turns out that we weren't able to realize exactly this, but sort of we were able to realize chain complexes that had sort of the same like necessary features. So we need to realize complexes like that. I think that's one reason why things like the moving or some of the because we have the tools computing on their okay, so what is the particular computational tool? So couple of years ago, I was talking about a formula for HF minus large cylinders. And then a couple of years later, they refined this for a formula for any surgery on a time. So this is via mathematical. So you take the number complex for your non-K, you build these subcomplexes, the co-complexes, and you take the math of the homology of that, spits out the Heegaard homology of circuit along your path. What is one actually the not for homology of the gradient? That was done by Matt. So, I guess here when I got the denominator, I thought about it as a chain of the group, two columns and two variables. We really need to think about the not giving a quotation on your chain how much variable. So, I guess Matt added over the beaver, putting a quotation on the result of 1. They gave a filter down. Or the not so complex. Here's the portion. Okay. Well, maybe one thing will complicate before, and so then Lynn studied so we can't love physical, so there's water surgery on your time. She was able to look at a table of what Hugo did is he combined this result and mathematics result to give a mathematical formula for cable of the gradient and right now, what the use in our theorem is, well, how to special your day, right? So, we use these numbers because of these computational tools for computing their advantage. You might wonder, well, wasn't actually capable of the derivative part? Actually, and in fact it was, because it turns out that meridians in surgery, those factors, they're sort of, they're not simple, but like you have particularly nice form that isn't enough to apply like some kind of object. So you really have to do something more complicated than the head of the main filter map. And so what thing that's more complicated you have to use, how special the cables, why don't you know the cables are particularly nice to study in the Heegaard world. So that's sort of the natural, like, more complicated thing to study, and then those examples. Thank you.